Hello everyone. Today let's solve the problem number 110, balanced binary tree. Right. So what the question states here, we are given a binary tree. See here, we are given a binary tree. We have to determine whether it is height balanced or not. When I hover over it, this one height balanced, the term height balanced, it says height balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than once. Right, the depth of the two subtrees of every node never differs by more than one. So that's what they have given here. See, it never differs by more than one, right? So here on this case, we have to return true. We have to return true. See here, see here. So again, I just want to tell you one thing before moving on to the second example here. So whenever we say this is height balanced, they have clearly mentioned that binary tree, this one height balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than one. Never differs by more than one. So this last line, this is very important. Every node never differs by more than one. Right. So this we have to keep in mind. A binary tree is height balanced if at every node the height difference between its left and right subtree is at most 1. We are given the root of the binary tree and we have to return true if the tree is balanced. Otherwise, we have to return false. Otherwise, we have to return false. Right. So example, we have for this one, just give me a second here. See here, again, let me tell you one thing here. We have this one here. This one is balanced, right? So this one is balanced because height difference is 1. So this one is 1 and this one is 1 and this one is for each it is 1, right? So it is 2. It is 2 for this one. For the right side, if you consider, this one will be 2, right? 0 1 2, right? So 2 minus 1, only 1 is the 2 minus 1 height difference we have as 1 for this one. So still this holds good. And for this one as well, this one as well, 15 and 7, it doesn't have children at all. For each the height, this one we can consider height of 1, right? So this will be 1 itself again. So we have maximum difference of 1 here. In this case, this remains true itself, right? So we have to return the value true. I hope this part is clear. Now let's come to the second example here. We have 2 here, this one, right? 2, this one, this is considered as 1. We don't have the right subtree at all for this one, and again for this one as well, this height as well, right? So here also we don't have anything here. Suppose from this side or this side, we don't have anything. So the height difference will obviously be more than 1 here. In this case, height difference will be more than 1 because 1 2 it will be. So 1 to 3 this will be 3 minus 1 it will be 2, which is greater than 1. So quite obviously the height difference will be more than 1. In this case we have to return false. In this case we have to return the boolean value false. If the third example is for the empty one, third example if, is for the empty one is always considered true. We have to always consider true if we don't have elements, if we don't have elements within the root, right? With if we don't have elements mentioned within the root, so in that case we have to return the output true, right? So just keep this in mind, right? So I hope the question part is completely clear. Now let's discuss the approach. Let's consider this example. You will get to know this one correctly, right? So let's discuss the approach followed by the complexities and then let's write the code. Let's discuss this example itself, man, right? So first we will start from the bottom, nothing but the node 9. So these are the bottom. This is bottom for the left and this is bottom for the right subtree. So right. So for the left, this is the bottom value 9 or the node 9, and for the right, the this one 15 and 7 are the bottom, right? So here we'll start from the bottom 9. Height equals 1 because this 9 is having no children, so height is 1 here. In this case, height is 1. So we have node 15 and 7 at the right, which is of the height 1 here. So this is also of the height 1 and this is also of the height 1 because it is not having any children here in this case. So we have node 20, left and right, height is 1. So see here, this one we are considering. So we are done with the 9, 15 and 7. Now let's go with the 20. 20 we have left subchild, left subtree and the right subtree. So 15, which is of the height 1, and 7, which is of the height 1. First node 9, height 1, node 15, height 1, node 7, height 1. So now this we have to consider this one, right? So this one we are considering because it comes under 20. So now we are considering 20. For 20 we have left and right height, means we have 15 and 7, right? So which is of the height 1, right? Which is of the height 1. So this is balanced, right? So height will be 2, which is balanced. Basically this 15 and 7, this is balanced, right? So this is of the height 2. This is of the height 2. Node 3, for the node 3, this one we are done with the 20 as well. Now let's go with the node 3. Now let's go with the node 3. Node 3 we have left 1 and right 2. Again, this one 9 and 20 we have. 9 and 20 we have, right? Both are of the height 1, right? Both are of the height, sorry, left height is 1, but the right height is 2 here. Right height is 2 here. 20, we have already got this one 2, right? Right height is 2 here, right? Right height is 2 here. So for 3, left height is 1, right height is 2, so this will be 1 minus 2. So this we have to go with a positive value always. So this will be minus 1, or we'll be considering this one 1 itself. We'll be considering 1 positive 1, or we can just go with the 2 minus 1. So we'll be going with the 1 minus 2, left minus right basically. So we'll be considering this one in the positive value itself. So the difference is 1 here. So the difference here is 1. So for the difference is 1 here. This part we have got 2, and the left part from 3, this one we have the height 1. So 1 minus 2, or this one will lead to difference 1. We can have the maximum difference of 1. They've strictly mentioned in the question to be balanced, right? So to be balanced, it shouldn't exceed more. This one 1, the value 1. So here we have got 1. So the tree is said to be balanced. So 3, this the difference is 1. We can consider difference. The value is always positive, so we'll be going with the positive value, right? Here the this one difference is 1, and it is said to be balanced. So whole tree is balanced here. Whole tree is balanced here. So nowhere we got this one, the value more than 1, or the difference more than the value 1, right? So here this is said to be balanced, and we will return the value true. We will return the value true, means we will return the boolean value true in this case. I insist you to try out with the second one. So you will get the this one height more, the difference you will get more. So you have to return false in that case. I insist you to try out with the second one so that you understand the problem correctly. So I have showed you for the example one. I hope the approach part is completely clear, man. I hope the approach part is completely clear. Now as we are completely familiar with the approach, let's do one thing. Let's discuss the complexities part. Let's discuss the complexities part. So what will be the time complexity? The time complexity would be big of n, because each node will be visited exactly once in the post order traversal. As I have said, we will be going with the post order traversal. We have already solved the problems on post order, in order, and this one pre order, right? So we should be knowing the orders of all the things: post order, in order, and pre order. So each node is visited exactly once in the post order traversal. So the time complexity would be big of n here in this case. So the space complexity would be big of h, right? So the space complexity would be big of h. So we will be going with the recursion. We will be going with the recursion, and we know that the recursion depth can go up to big of n. Recursion depth can go up to big of n. So here I have given h because it is safe. We have to consider the worst case, and for the worst case we will always consider for the skewed tree. So h is nothing but the height of the tree. We will be going with the big of h here in this case. So the space complexity would be big of h. The time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of h, right? So this is it for the complexities part. As we are completely familiar with the complexities and this one, what do we call uh, approach, now we are good to write the code. Let's start writing the code. Initially, if you remember what we need to do, so basically if the tree is not balanced, we have to return -1. Just keep this in mind. We didn't discuss this one earlier. So if the tree is not balanced, then we have to return -1 in this case, right? So just keep this in mind. So this is fine. To check this one whether this is balanced or not, let's go with the helper method. Let's go with the helper method. So I'll just go with private int the helper method check weight. So this will be check weight of this one will be tree node of node. This is fine. So I'll just come with an sorry, let's continue with the further things. So base case is if the height of the node is null, then we have to return 0, right? If the height of the node is null, then we have to return 0 at that case. So this is given in the question itself, right? So in the third example they have mentioned, see here, this one, if the height of the node is null, then we have to return 0. So here node equals null, then we have to return 0. This is fine. This is base case. And next step is, as I've said, we'll be going with the recursion. Means we'll recursively get the height of the left subtree first. So I'll just go with int left equals, let's go with the function name or the method name here, check height. First node dot left, then if the left subtree is not balanced, then we have to return -1, right? So we have discussed this one, we should be knowing this. So this one will be, if left equals -1, then we have to return -1 itself. So here it will be return -1. This is fine. So let's move on with the right subtree. So here let me copy this one, let me paste this one. So here it would be right, int right equals check weight of this one, node dot right. This is fine. If instead of left, I'll just make this one right. If the right subtree is not balanced, then we have to return -1 as well. So this is fine. We are done with this one, right? So line number 12 and line number 9, what we are doing? Here we are recursively getting the height of the left and right subtrees. So I hope this part is clear. This is very easy to understand, man. Right? So whenever we are making use of the recursion, it's easier. So unless the constraints are very tight and we have been asked to solve the problems iteratively, unless the constraints are, again I'm repeating this one, unless the constraints are very tight and we are strictly asked to solve the problems iteratively with stack, it is better to use the recursion. The code will be very easy comparatively with the iteration. So the code will be very easy comparatively with the iteration part, right? So next let's move on with the further things. So now if the current node is not balanced, then also we have to return -1. So let's write the simple if condition here. This will be math dot absolute here. I'll just give abs. So this one will be left minus right. This is fine. So if this is greater than 1, then we have to return -1. Then we have to return -1, nothing but here if the current node is not balanced, then we have to return -1. So we have to return the height if it is balanced tree. If it is a balanced tree, we have to return the height if it is a balanced tree. So here on this case, as the binary tree indexing starts from 0, we will add +1, right? So this will be written 1 plus math dot max of this one, left comma right. Again I'm telling this part 1 plus, because the binary tree indexing starts from 0. Binary indexing starts from 0 and we need the solution in one index, basically not one indexed in the terms of one, it has to start from one basically, right? So that is the reason we are going with one. You can consider in that way itself. Binary tree indexing starts from 0, so we are going with +1 here, 1 plus math.max of left comma right. So I hope this part is completely clear. Don't get confused why we have written 1 plus here, for why we have written 1 plus here. This is fine. We are done with the helper method check weight. Now let's make use of that helper method within the main function is balanced. So I'll just go with return here. This will be, we will be making use of this function or this method, right? So this will be check weight of root, so not equal to -1, not equal to -1. Let me do one thing. Yeah, this is fine. So not equal to -1 means if -1 is written, then the tree is said to be not balanced. Tree is said to be not balanced or unbalanced here, this one, right? So tree is said to be not balanced here in this case. Let me format the code once. Let me hit the run button. So this is it for the code, right? This is it for the code. Simple, right? So you can clearly see here the sample test cases are getting passed. Means let me hit the submit button. So here you can clearly see all the test cases are getting passed, means the code works absolutely correct in this case. The code works absolutely correct in this case, right? So for now, I hope the solution part is completely clear along with the approach and the complexities, right? For now, this is it. Thanks for watching, guys.